Hello everyone, I am Rupokde. Today I am going to discuss a problem on functional analysis which is asked in GATE 2018, and this same type of question is also asked in GATE 2020 also. So functional analysis plays an important role for GATE exam and many others exam also. So let's try to understand this kind of problem first, and after that we will try to solve it. Okay, so here given problem is, let L2 close interval 0 and 1 be a Hilbert space of all real valued square integrable function on close interval 0 and 1 with the usual inner product. Let phi be the linear functional on L2 close interval 0 and 1 defined by phi of f is equal to integration 1/4 to 3/4 3 root 2 f d mu, where mu denote the Lebesgue measure on closed interval 0 and 1. Then we have to find what is the value of norm of phi. Okay, so we have to find the value of norm of phi. So here also given that L2 closed interval 0 1 be a Hilbert space. Now what is Hilbert space? And when we discuss about the Hilbert space, we should discuss first what is the inner product space. Okay, so what is the inner product space? When we discuss about inner product space, then here we consider a non-empty vector space over a field that may be R, may be C. Okay, so X be a non-empty vector space over field if this may be C, this may be R. Now we define a mapping. Such that X cross X to F which satisfy three conditions. Okay, so first condition is non-negative definiteness, and second condition is conjugate symmetry, and third condition is also linear with respect to first argument and linear with respect to second argument. So what is the condition of non-negative definiteness? Okay, so X and X greater equal to 0 for all X belongs to X, and X not X is equal to 0 if and only if X equal to 0. So inner product of X and X always greater equal to 0 for all X belongs to X, and X not X is equal to 0 if and only if X is equal to 0. So this is the condition of non-negative definiteness. Now what is condition for the conjugate symmetry? For X and Y, inner product of X and Y is equal to inner product of Y and X bar for all X and Y belongs to X, and this is the condition of the conjugate symmetry. And number 3 is first linear with respect to second argument. Now we consider X and alpha Y plus beta Z. This is equal to alpha of X and Y plus beta of X and Z. Clear? This is linear with respect to second argument. Clear? And alpha X plus beta Y and Z is equal to alpha bar X and Z plus beta bar Y and Z. This is also linear with respect to first argument. If a mapping satisfy these three conditions, then we say that this mapping is also the inner product, and X with this inner product is also called the inner product space. Clear? Mapping is also called the inner product, and X with the inner product is also called the inner product space. And when this inner product space is complete, then we say that this is also the Hilbert space. So Hilbert space is also the complete inner product space. Clear? And we denote by complete inner product space is called the Hilbert space, and we denote Hilbert space by H with inner product. This is also called the Hilbert space. And if H be the Hilbert space, then this is also a vector space, and this is also a topological vector space, and this is also a nonlinear space, and this is also inner product space. I don't discuss about what is vector space, what is topological vector space, what is nonlinear space, because if I discuss here, then video become too lengthy. So if you don't know what is the vector space and what is the topological vector space and what is the nonlinear space, then you see any standard book, okay, and clear your basic concept. So this is the Hilbert space, and if H be the Hilbert space, then this also the vector space and topological vector space and nonlinear space and inner product space. And when a metric space is called the Hilbert space, when we say that a metric space is called the Hilbert space, when if a metric space is complete, then we say that this is the Hilbert space. So complete metric space is also called the Hilbert space, and dimension of the Hilbert space may be finite and may be infinite. That does not matter. Okay, so complete metric space is also called the Hilbert space. Clear? So this is the concept about the Hilbert space. Now here also given that L2 closed interval 0 and 1. Now what is L2 closed interval 0 and 1? L2 closed interval 0 and 1 is also set of all Lebesgue integrable function on closed interval 0 and 1 such that integration over closed interval 0 and 1 mod of f square d nu less than plus infinity. So this is the L2 closed interval 0, 1, the set of all Lebesgue integrable functions such that integration over x mod of f square d mu less than plus infinity. Okay, so here mu is the Lebesgue measure on closed interval 0 and 1. Clear? So this is the L2 closed interval 0, 1, and this L2 closed interval 0, 1 is also called the self dual. Clear? And this is also called the self conjugate also, and this is also called the Hilbert space also. Clear? So L2 also the self dual, it is also the self conjugate, and it is also the Hilbert space as well as also. So L2 closed interval 0 and 1 with the Hilbert space of all real valued square integrable functions with closed interval 0, 1 with usual inner product. And what is the real usual inner product in the Hilbert space L2 closed interval 0 and 1? The real inner product x and y is equal to integration over x, that is equal to closed interval 0 and 1 xt yt dt, that is also real usual inner product. Clear? And what is norm of the function on L2 closed interval 0 and 1? The norm of the function also defined as norm of f2 is equal to integration mod of f square d mu to the power half. This is the norm on the L2 closed interval 0 and 1. Clear? And here also given that phi be the linear functional. So a functional is called linear when it satisfies the linear property as well as also. Okay, so phi be the linear functional on L2 closed interval 0 and 1 defined by phi of f is equal to integration 1/4 to 3/4 3 root 2 f d mu, where mu denotes the Lebesgue measure on closed interval 0 and 1. Then we have to find that what is the value of norm of phi. Clear? Now let's try to solve this kind of problem, and I always start with how to solve this kind of problem. Okay, so how to solve? So how to solve? Recall a theorem that is also called Ries representation theorem. Okay, so what is Ries representation theorem? H be the Hilbert space, and phi be a bounded or continuous linear functional on H, that is phi belongs to H star. And what is H star? H star is the dual space of the H, and this is also the set of all continuous and bounded linear functional on H, also denoted by H star. Okay, so that is phi belongs to H star. Then there exists a unique G belongs to H such that phi of f is equal to inner product of f and g for all f belongs to H. Then norm of phi with respect to H star is equal to norm of g with respect to H. That is, there are 1:1 correspondence between H and H star. Clear? So H be the Hilbert space and phi be the bounded or continuous linear functional on H, and phi, that is phi belongs to H star. Then there exists a unique G belongs to H such that phi of f is equal to inner product of f and g for all f belongs to H. Then norm of phi H star is equal to norm of g with respect to H. So that is, there are 1:1 correspondence between H and H star. So this is the Ries representation theorem, and here we use the Ries representation theorem to solve this kind of problem. Clear? And here also first condition also given that H be the Hilbert space, and here L2 closed interval 0 and 1 be the Hilbert space. And second condition is also phi be the bounded or continuous linear functional on H. Here also given that phi be a linear functional on the Hilbert space L2 closed interval 0 and 1. So first we have to prove that phi is a bounded linear functional on L2 closed interval 0 and 1. Okay, so we have to prove phi is bounded in L2 closed interval 0 and 1. Now, what is norm of phi? This is equal to integration over x equal to 0 and 1 mod of phi square d mu to the power half. Clear? And what is phi of f? Phi of f is equal to this. Clear? And this is equal to integration 1/4 to 3/4 3 root 2 f square d mu to the power half. Clear? And this is equal to 3 root 2 1/4 to 3/4 mod of square 2 to the power half. Clear? Now f belongs to L2 closing interval 0 and 1. That means integration over x closing interval 0 and 1 mod of f square d mu less than plus infinity. Clear? So that means integration over 1 by 4 to 3 by 4 mod of f square d mu also less than plus infinity. Clear? So this is less than plus infinity and this is a constant function, so this is less than plus infinity. So that means phi is bounded in L2 closing interval 0 and 1. Since phi is bounded in L2 closing interval 0 and 1, that means phi is continuous in L2 closing interval 0 and 1, because you know that in a linear functional on a nonlinear space is continuous imply bounded and bounded imply continuous. Okay, so that is a linear functional on a nonlinear space. If it is bounded, that means that is continuous. If linear functional on the nonlinear space continuous, that simply bounded. Okay, so and you also know that Hilbert space is also a nonlinear space, so here this condition is also hold. So if phi is bounded in L2 closing interval 0 and 1, that means phi is continuous in L2 closing interval 0 and 1. Clear? So that means also phi is a linear functional. That means phi is a continuous or bounded linear functional in L2 closing interval 0 and 1. Clear? So phi is a continuous and bounded linear functional in L2 closing interval 0 and 1. Now to find what is the function g. So here phi of f is equal to integration 1 to 4 to 3 by 4 3 root 2 f d mu. Clear? And this is equal to 1 by 4, this is equal to 0 to 1 by 4, 0 into f d mu plus 1 by 4 to 3 by 4, 3 root 2 f d mu plus 3 by 4 to 1, 0 into f d mu. Clear? Now this is equal to inner product of f and g for all f belongs to h, that is equal to L2 closing interval 0 and 1. Now we define a function. G on x is equal to closing interval 0 and 1 by g of x is equal to 0, 0 less equal to x less than 1 by 4 and 3 root 2 1 by 4 less or equal to x less or equal to 3 by 4 and 0 for 3 by 4 less than x less or equal to 1. So now you construct a function gx on closed interval 0 to 1 by this way. Okay, now we have to find what is the norm of g. Okay, now we have to find what is the norm of g. Now norm of g 2, that is equal to integration over x equal to closed interval 0, 1 and mod of g square d mu 2 to the power half. Clear? And this is equal to integration 0 to 1 by 4 0 into d mu plus 1 by 4 to 3 by 4 3 root 2 a whole square d mu plus 3 by 4 to 1 0 into d mu to the power half. Clear? Now this is equal to integration 1 by 4 to 3 by 4 3 root 2 a whole square d mu to the power half, and this is equal to 3 root 2 into 1 by 4 to 3 by 4 d mu to the power half, and this is equal to 3 root 2 into 3 by 4 minus 1 by 4 to the power half, and this is equal to 3 root 2 into 1 by root 2. Okay, and this is equal to 3. So we find that norm of G2 is equal to 3 and that this is equal to norm of phi. So this implies norm of phi is equal to 3. Clear? Therefore then norm of phi is equal to 3. So this is the way to approach this kind of problem, and you do not able to solve this kind of problem in the exam hall for the lack of the basic concept. So focus on the basic concept. If your focus, if your basic is too good, then you feel comfortable for this problem as well as also. So now we discuss another problem which is also asked in GATE 2018 on the function analysis. Today I am going to discuss a problem on functional analysis which is asked in GATE 2018. So let's try to understand this kind of problem first, and after that we will try to solve it. Okay. So our problem is also, let U be an orthonormal set in Hilbert space H, and let x belongs to capital H be such that norm of x equal to 2. Consider the set capital E is equal to U belongs to capital U such that modulus of inner product of x and u greater or equal to 1 by 4, then the maximum possible number of element in E is. So now we have to find that the number of element in the set, the maximum number of element in the set E. Clear? Here also given that U be an orthonormal set and capital U be an orthonormal set in the Hilbert space, and I discussed what is the Hilbert space in the previous video also, and here also given that x belongs to H be such that norm of x equal to 2. Now U, here also given that U be the orthonormal set and small u belongs to U. That is, if I consider Ui and Uj belongs to U, then we say that Ui and Uj are two orthonormal set if Ui, inner product of Ui and Uj, is equal to 0 if I not equal to j, and 1 if I equal to j. If the orthonormal set, orthonormal vector, or the two orthonormal vector Ui and Uj satisfy these conditions, then we say that the two vector Ui and Uj are orthonormal vectors. Okay. Now we have to find the maximum number of elements in the set E. So how we approach this kind of problem? So I always start with how to solve this kind of problem. So how to solve? First, recall some basic fact. Number 1, Basal inequality. For infinite dimensional inner product space. So what is the Basal inequality for the infinite dimensional inner product space? So let EI I equal to 1 to infinity be the orthonormal sequences in the inner product space capital X. So I equal to 1 to infinity be the orthonormal sequences in the inner product space X. Okay. Now for all x belongs to X, I equal to 1 to infinity X EI square less or equal to norm of X square. So this is the Basel inequality for the infinite dimensional inner product space. So summation I equal to 1 to infinity modulus of xi and ei inner product modulus of inner product of xi and ei square less or equal to norm of X square. So this is the Basel inequality for the infinite dimensional inner product space. Now what is the Basel inequality for the finite dimensional Hilbert space? Okay, so let H be a Hilbert space and I equal to 1 to n be the orthonormal set of vectors in H. Clear? Then for x belongs to H, summation I equal to 1 to n modulus of x inner product of x and ei square less or equal to norm of X square. Clear? So this is the Basel inequality for the finite dimensional Hilbert space. So this is the Basel inequality for the infinite dimensional inner product space and this is the Basel inequality for the finite dimensional Hilbert space. And proof left for exercise, please do yourself. Okay, if you don't able to prove it, please write in comment box. I definitely try to help you. Clear? So now here use the finite dimension Basel inequality for the finite dimensional Hilbert space to solve this kind of problem. Clear? Okay, now let's try to solve this kind of problem smoothly. So given that E is equal to this. Clear? So E is equal to U belongs to capital U such that modulus of inner product of x and u greater or equal to 1 by 4. Clear? Now we have to find what is the maximum possible number of elements in E is. So let the number of element, the maximum number of element in E is n. Clear? So I says that let the maximum number of elements in the set E is equal to n. Then E equal to ui belongs to u such that x and ui greater or equal to 1 by 4 for I equal to 1 to n. Clear? Then E becomes this. Now ui belongs to u and x and ui this is equal to 1 by 4. This implies squaring both sides we get 1 by 4 square. This is equal to 1 by 16. Now take summation I equal to 1 to n x and ui square. This is equal to summation I equal to 1 to n 1 by 16, that is equal to n by 16. Clear? Therefore I get summation I equal to 1 to n modulus of inner product of x and ei square. This is greater or equal to n by 16. So this is number 1. Clear? Now we use the Basal inequality for the finite dimensional Hilbert space. What is the Basal inequality for the finite dimensional Hilbert space? This is equal to summation I equal to 1 to n x and uy square. This is less or equal to norm of x square. And here also from given question we find that norm of x is equal to 2. So that is equal to 2 square, that is equal to 4, and this is number 2. And combining these two inequality we get n by 16 less or equal to summation I equal to 1 to n x and uy square less or equal to 4. Clear? And this imply n by 16 less or equal to 4. Clear? And this imply n less or equal to 64. So the maximum possible number of elements in E is equal to 64. Clear? So this is the way to approach this kind of problem, and I hope you got the idea. See here, today I discuss 2 problems on related to the functional analysis, and this is too easy problem, but you cannot able to solve this kind of problem in exam hall because for the lack of the basic concept. So basic is here very important. So first clear your basic. If your basic is not good, it's not a crime. Anybody don't know everything. Clear? I also don't know many things, but I always try to learn every times. So try to learning, follow any standard book, clear your concept and make your fundamental good, then you feel comfortable to solve this kind of problem. Okay, so this is the way to approach this kind of problem, and subscribe my channel for more update, and again thank you.